I'm going to start with an introduction about CMB polarization. I will then present the present and future of CMB observations for what is related to B-modes. And then I will go a bit more in details about one of the greatest challenges that we have in CMB experiments, which is the contamination coming from galactic foregrounds. In the last part of the talk, I'm going to present some results that I obtained on a project that I've been working in the last week, which is related to the use of neural networks to try to extend the current model that we have for galactic foregrounds. So I guess the majority of you knows what CMB is, but let me give a quick reminder just to put everyone on the same page. So the standard model of the evolution of the universe states that in the very first stages of the evolution of the universe was in a status of very hot and dense plasma, where radiation and matter were highly coupled due to Thomson and Compton scattering. The universe expanded, and about 380,000 years after the Big Bang, the temperature of the universe was low enough, about 3,000 Kelvin, to allow the formation of the neutral atoms. And in this way, the cross-section of the scattering dropped, and photons were free to propagate. So these photons are still propagating in the universe, and as the universe expands, they are redshifted and are today in the range of the microwave. Of course, photons in the primordial universe were present, were filling the whole universe and were propagating in all the directions, and they still do. And from our point of view, we can observe these photons as coming from a surface, a spherical surface around us that we call the last scattering surface. So this is the surface where the photons of the CMB last scattered with the free electrons in the primordial universe. This is the standard picture of the evolution of the universe that I'm sure that you've seen several times. So these are the first stages where, as I said, the universe was in a plasma state. This is the last scattering surface from which the CMB was started to be emitted. And here you see a map of the CMB total intensity. This is the sphere that I told you about projected on a map. The CMB is highly homogeneous with a black body spectrum at a temperature of about 3 Kelvin, and there are anisotropies which are the level of 1 part over 10 to the 5. And here you can see these anisotropies that can be thought as the seeds of the structure that we observe today. So by looking at the CMB, we can learn a lot of things on the primordial universe, so this part of the evolution of the universe, as well as things about the evolution of the later evolution of the universe, as the CMB photons interact with the structures that were formed in our universe. One of the important feature in the CMB is that CMB is polarized. This is due to the fact that Thomson scattering actually polarized radiation, and the outcoming radiation is linearly polarized with polarization which is parallel to the incident one. Of course, one electron in the primordial universe was scattering radiation coming from several directions. So if we don't have any kind of anisotropy in this radiation that was scattering on the electrons, then we cannot get any final net linear polarization, as all the effect will cancel out in the different directions. If in the primordial universe there were a kind of anisotropy, and in particular a quadrupole anisotropy with radiation coming from orthogonal direction with some differences, then at the end we can have a net linear polarization in the CMB signal. Of course, not all the electrons were scattering radiation in presence of this quadrupole anisotropy. Only those electrons which was scattering radiation in an optically thin region. So the CMB is not 100% polarized, but the fraction of polarization is pretty small at the level of 10% or even less. This means that the polarization signal is at the level of micro K or even below. So observing the CMB polarization is pretty challenging. We need high sensitivity. So we can observe this polarized signal, and what we do with our experiments is that we measure the standard Stokes parameters, so the Stokes Q and U that define the linear state of the polarization of the radiation. From the Stokes Q and U, we can obtain the total polarized intensity, this P that you can see here, and the polarization angle, so the orientation of the polarization. And basically, we can build a kind of pattern of polarization in the sky that you can see here. So each line here tells you how much the signal is polarized in each point of the sky. So this is the length of the segments that you see here and the orientation of this polarization. One other thing that we can do is that we can divide this polarization pattern into a different base. These are the so-called E-modes and B-modes. A way of seeing that is that these two different modes have different geometrical properties. In particular, the B-modes are those modes which are odd under parity inversion. So you can see the pattern, the geometrical pattern here. If you think about applying a parity inversion, you see that you flip the sign. You go from positive to negative and vice versa. The E-modes can be thought as those patterns that are even under parity inversion. If you apply a parity inversion here, you don't change nothing. The sign doesn't flip. So this is a way of seeing these two different modes in the CMB polarization. The important thing is that we can actually find the relation between the geometrical properties of these modes that we observe in the CMB pattern and the geometrical properties of the quadrupole anisotropy in the primordial universe that we are generating at the first time the CMB polarization. So as I said, to generate a net signal, we need a quadrupole in the primordial universe, and so we have three different geometrical patterns. The scalar perturbation, which are the one with m equals 0, that can be that have this pattern and can be generated by density wave in the primordial plasma. Then we have vector perturbation with m equal plus or minus 1, and these can be generated by the presence of vorticity in the primordial plasma. And finally, we have the tensor perturbations, the one with m equal plus or minus 2. And these, it's pretty easy to show that this kind of pattern can be generated by the presence of primordial gravitational waves. So we have three different geometrical patterns in the primordial plasma, in the quadrupole anisotropy in the primordial plasma, and then we have two geometrical patterns in the CMB polarization signal. And it can be shown that the scalar perturbation cannot generate anything which is odd under parity inversion. So the scalar perturbation can generate only what we call the E-modes. The vector perturbation in principle could generate both E-modes and B-modes, but in the standard scenario, we think that vorticity are damped by the universe expansion. So we are left with tensor perturbation that can generate both something even and odd. So they can generate both E-modes and B-modes. So you see here that the only kind of perturbation in the primordial universe that can generate B-modes are the presence of primordial gravitational waves. But what generated these gravitational waves in the primordial universe? Well, the theory of inflation that, as you might know, was developed in early 80s. And actually, it was introduced to somehow explain some of the features that we observe in our universe, especially the flatness of the universe and the fact that the CMB is so homogeneous. And so it was somehow introduced a posteriori to explain what we were observing in our universe. But the inflationary theory, which predicts a phase of exponential expansion in the very first stages of the evolution of our universe, so this theory predicts also the presence of quantum perturbation in the metric of primordial universe, which are actually gravitational waves that are stretched at microscopic length due to this exponential expansion. So the point is that inflation predicts this gravitational wave that should have left a signature in the B-modes. So if we manage to observe this B-mode pattern in the CMB polarization, then we would have the first experimental proof that inflation really happened. This is why observing B-modes is so important. The last point is that the CMB field is highly Gaussian, almost perfectly Gaussian. This means that all the statistical informations are encoded in the two-point correlation function or in the Fourier transform of it, which is the power spectrum. So we have three fields. We have the total intensity, what we call the temperature of the CMB. We have the two modes for polarization, E modes and B modes, and we can compute the power spectra. So we have the TT, EE, and BB that you see here, and of course we can also have the cross correlation of the different fields. So the TE, and TB, and EB power spectra that I'm not showing here for simplicity. So by studying this power spectrum in the different region that you see in this plot, let me underline that in this plot you have the amplitude of the fluctuation in the CMB field as a function of multiple, which is inversely proportional to the angular scale. So where you are at high multiples, it means that you are looking at the very small angular scale, and on the other hand, if you look at low multiples, you are looking at the very large angular scale in the sky. A multiple of about 180 correspond to an angular scale of about 1 degree in the sky. So we have this power spectra, and this is the B modes power spectra, so the one that we are interested in. Actually, you see that the B modes power spectrum coming from primordial gravitational waves have this shape that you see here with these two dotted lines. And you see that I have put two different lines in this plot because the amplitude of this primordial B-mode spectrum is actually parameterized with the parameter R, what we call the tensor to scalar relation, which is nothing else than the relation between tensor and scalar mode in the primordial universe. So this is the parameter that we want to constrain, and it is important to constrain because it is directly linked to the energy of inflation. So if we manage to constrain the value of R, then we can learn something about inflation, and we can distinguish among the different inflationary paradigms that exist, and that gives you different value of R. So we have this primordial B-modes power spectrum, but we also have a secondary kind of B-modes power spectrum that you see here, which is coming from lensing. So this is due to the interaction of the CMB with the structure, the gravitational structure in our universe, and this lensing somehow cause a leakage between E modes and B modes, causing the power spectrum that you see here. So when we want to observe the primordial power spectrum of the B modes, then we need also to remove this lensing, as I will tell you at the end of this talk. Another important thing about the power spectrum of B modes is that we have two different bumps. You see it here. One bump is at the angular scale of about 1 degree, while the second bump is at much larger angular scale of the order of tens of degrees in the sky. So just to summarize, we have this quadruple anisotropy in the primordial plasma that can generate linear polarization. We observe this linear polarization in the CMB field that we divide into two different modes accordingly to their geometrical properties. And only the tensor perturbation, the gravitational wave in the primordial plasma, can generate B modes. And we can study all of these just by computing the power spectra of the CMB maps that we obtain. So where we are with this CMB observation, so we couldn't observe the primordial B mode signal yet. We have an upper limit on the value of R that you see here, which is at the level of 0.06. This is coming from the bicep Keck observation in combination with Planck 1. So we are somehow entering in this period a new phase in the CMB observation. We have a lot of ground-based experiments which are trying to observe this primordial B-mode signal. And we are also in the phase where we are starting, actually we have started already to design and build a new satellite experiment. So right now for the CMB observation, we are somehow in the phase where we were about 50 or 20 years ago for CMB total intensity observation. So before the launch of WMAP and Planck. Here, just to let you understand how difficult it is to observe these primordial B-modes, I'm showing some simulated maps. So this is the total intensity, the unpolarized radiation of the CMB. This is the full polarization pattern, polarization radiation that we observe. And you see that here the color bar, the color scale is shrink already by a factor 100. But then if we consider only B-modes, you see that basically we cannot observe nothing with this color scale. So the B-modes are really much smaller than the E-modes, so at the level of some nano-K. So these observations are really challenging. So this is where we are with observations, where we have some experiment that managed to observe and to detect the gravitational lensing signal, but no one managed to observe and to detect the primordial B-mode signal. And in the second plot, you can see the situation where we hope to be in, let's say, 10 years from now. And you see that we have in particular a couple of experiments. I will talk you about them in a minute. And with these two experiments, we think we can put constraint on so very stringent constraint or to observe the primordial B-modes. And you see that here we managed to reconstruct the large angular scale bump in the CMB power spectrum. So these two experiments are two of the experiments that are already almost fully founded. So in principle, they should really happen in the next, let's say, 10 years. One is the Simons Observatory. This is the ground-based experiment, which will be located in the Atacama Desert in Chile. It's going to have 4 different telescopes observing in 6 bands, frequency bands, and I will tell you in a minute why we have so many frequency bands in CMB observations, with a sky coverage between 10 and 40%. So from the Earth, we cannot observe the full sky. And so the Simons Observatory will be able to observe the CMB at intermediate and high and small angular scales. So this blue point that you see here. And the baseline design is thought to reach an accuracy on the tensor to scalar ratio R at the level of 3 10 to the minus 3. Then we have a space mission which was selected last year by the Japanese space agency, which is called LIGHTBIRD. Of course, being a space mission, LIGHTBIRD will cover the full sky and will focus on the very large angular scale. So being able to constrain this part of the power spectrum. Here we will have a lot of bands, 15 frequency bands, and the goal and the forecast says that we will be able to reach an accuracy on R at the level of 6 10 to the minus 4. So about 2 orders of magnitude below the current upper limit that we have on the primordial B-modes. So why so many frequencies in CMB experiments? Well, CMB experiments at this point are not limited by sensitivity, although even if the signal, the B-mode signal, as I said, is really faint, we know that we have, in the current status, we have enough sensitivity in our CMB experiment to be able to observe it. The limiting factor here is actually the contamination coming from other sources in the sky emitting in the microwave range. And in particular, in our galaxy, we have 2 strong kind of emission which are polarized, the synchrotron and the thermal dust. So the synchrotron is coming from, of course, the acceleration of the cosmic ray electrons in the galactic magnetic field, is intrinsically polarized with a polarization fraction that can reach up to 20%. And it has a frequency dependence which goes as a power law and dominates the sky at the very low frequency, so at low frequency, so below about 70 gigahertz. On the other end of the spectrum, we have the thermal dust, which is the thermal emission of the dust grains that we have in the interstellar medium. And the fact that these grains are asymmetric and they tend to be aligned to the galactic magnetic field creates a linearly polarized signal, which could be pretty strong at the level of 20% again of polarization fraction. The thermal dust has a different frequency dependence, going as a modified black body, and it dominates the spectrum at the high frequency, above 100 gigahertz. So here you see the behavior of the two emissions, the synchrotron dominating at low frequency, the thermal dust dominating at the high frequency. And you see that they dominate over the CMB everywhere. In order to, one important thing that I like to highlight is that this is the first plot that we have about the CMB, with the first observation of the CMB in the 60s. And you see that in this first plot that we had, there is a line showing the galactic foregrounds. This is because already since the beginning, we know that foregrounds could be a problem. But here I show you somehow the level of awareness and concern about the contamination coming from galactic foregrounds in the years. So let's say that until 5 or 6 years ago, we were pretty convinced that there were regions in the sky where the foregrounds were low enough to allow to detect the primordial B-modes without taking into account them. Then in 2014, there was this BISOP observation, which claimed to measure the first time measurement of the primordial B-modes. But in few months, we realized that actually this measurement was coming from galactic dust. So since then, we started to realize that we really need to take into account foreground everywhere in the sky, so we cannot claim any B-modes observation without taking into account foregrounds, both for dust and synchrotron. And I would say that in the last couple of years, we reach a pretty high level of anxiety about that, and we are fully aware that this is our biggest challenge in CMB observations. Here, I show you again this. So in this map, you see the minimum level of foreground contamination in a region of the sky which covers a sky fraction of about 1%, so pretty small region in the sky. And this is expressed in terms of equivalent R. So is the R that you would measure, but coming from foregrounds, not from primordial B-modes. And you see that there is no region in the sky, at least in this part of the sky that you can see here, but we do not expect the situation to be different in the remaining part of the sky. So you see that there is no region where the contamination coming from foregrounds is below 10 to the R 10 to the minus 3, which is our goal for the next generation of CMB experiments. And in these plots here, you see that as we move in frequency, so at the low frequency, we are dominated by synchrotron. At the high frequency, we are dominated by thermal dust. But at intermediate frequency, there is no a window where both synchrotron and thermal dust are low enough to not be considered. We always have to consider both these kind of emissions. And so what we do is what we call component separation. So we try to remove the contamination coming from galactic foregrounds to get a clean CMB map that we then use to obtain power spectra and to constrain the value of the tensor to scalar ratio. So basically, the assumption that we do is that each map that we observe is nothing else than a combination with a mixing metric of the different sky components, so both foreground and CMB, and then of course we have noise. So to get a clean CMB map, we need to obtain this mixing metric in the different regions of the sky and just invert this equation. So basically what we do, or what we try to do, is to combine all the different map at different frequency that we have. Here you see the 9 frequency coming from Planck, and to combine them in order to solve this problem and to get a clean CMB map. So for this reason, we need a lot of frequency in order to be able to do this game in a very accurate way, because we want the residual to be really small. So these were the 9 Planck frequency. For example, in LIGHTPER, we're going to have 15 frequencies in order just to do this component separation in the right way. So one of the problems that we have in dealing with this challenge of removing foregrounds is that we don't have very accurate model for foreground emission. Actually, all the data that we have and the model that we are using right now are based on this data, are coming from the full sky observation of WMAP and Planck. In particular, for thermal dust, we can rely only on the full sky observation of Planck at the high frequency in polarization, 353 gigahertz, and this frequency is reliable only, at least on the full sky, is reliable only at angular scale larger than 1 degree. If we go to smaller angular scale, then we are too contaminated by noise. For synchrotron, we can rely on WMAP and Planck data, but again, the sensitivity is not good enough, so we can use this data only at angular scale larger than about 3 degrees. Of course, we would like to have better model and also the smaller angular scales. The problem is that we won't have any new data until we will deploy our new experiments. So we won't have new data on which to test our component separation algorithm in order to get prepared to do this component separation until we will actually deploy our experiments. So nonetheless, we need model because we need to get prepared. We need to test our foregrounds, our component separation algorithm. So how can we do that? Well, this is a basic wish list of the foreground model, of the properties that a good foreground model should have. Of course, we would like a good model to have the right amplitude of foreground emission and the right morphology on the large scale, and this is something that we have thanks to Planck and WMAP data. But we want, of course, also to have the model to reproduce at least the statistics of foreground at small scales, as I will show you in a minute. Then we would like to know what's the global frequency dependence of the two kind of foreground emission, and also what's the spatial variation of this frequency dependence, so how this vary in the sky, because we do not expect it to be the same in all the region of the sky. I could talk about all of these points about foregrounds, but I'm going to focus only on this second point. So the fact that we would like to have small scale foreground models. Why we would like to have that? Well, here you see the plot that I showed you before, but I put a new line here which show you the contamination coming from foregrounds, and you see that the foregrounds are above the tensor modes that we want to observe from the primordial universe, but they contaminate also at the small scales the lensing potential. And as I told you before, to be able to reconstruct this power spectrum, we first need to reconstruct the lensing power spectrum and the lensing potential, and to delens our maps in order to be able to get to this signal here. So we want to understand how the foreground contaminates also lensing at the small scales. And the point, as I told you before, is that our models are available only at angular scale at about 1 degree. So in this region of the sky, in this region of this plot here. And what we do right now is that basically we get the power spectra of these foregrounds emission, and then we extrapolate them with power laws, basically. And then what we do is that we generate map as a Gaussian realization of these power spectra. Of course, this is not the best choice, as we know that foreground are emitted in a complicated way, and they for sure are not Gaussian. And we want to understand, and we want to have model where this non-Gaussianity is present, because we want to understand how this non-Gaussianity contaminates the lensing reconstruction. We don't have data, as I said, and also the simulations that we have, the magnetic hydrodynamic simulations, are not, let's say, mature enough to be plugged in our model. So one thing that I've tried to do in the last weeks, in the last month, let's say, is to try to use neural network to add realistic non-Gaussian small scales to our current model of the galaxy. And the code that I'm developed is called FORSE, and which stands for foreground scale extender. So the general idea is to train a neural network on the region where we have data, also at small scales, because at least for dust, if we just look close to the galaxy where the signal is much higher, then we have some regions where the data are good enough to be trustable also at the sub-degree scale. So in this region of the sky, we can train a network to understand the relation between the large scales and the small scales, and to understand which is the statistics of these small scales. And once this neural network is trained, then we can apply it to other regions of the sky where we only have data at large scale, so let's say at about 1 degree, and try to get a realistic simulation of foregrounds also at small scales, also where we don't have data. So this is the general idea of this code, and the way we are able to do that is by using this particular kind of neural network. So I'm not going to go into details, but this kind of neural network, which are called GANs, generative adversarial neural network, are somehow they're composed by two different networks. One is the generator, one is what is called the discriminator. So the generator, what the generator does is that it takes as input a patch of the sky observed at the large scales at 1 degree, and it tries to generate small scales starting from this large scale structure that we give to it. At the same time, we have some data at some real data at a sub-degree scale. So the goal of the discriminator is to distinguish the small scales which are real, coming from real data, and the small scale which are coming from which are generated by the neural network. So in this way, if we put together these two different neural networks and we let them fight against each other, at the end, we will get a generator which generates small scales good enough that the discriminator cannot distinguish what is real and what is fake anymore. So when we are able to reach this equilibrium, it means that the generator is able to produce small scales which are realistic. So this is the general idea. Here you see some preliminary results in total intensity. So here you see the input of our neural network. So this is a patch of dust in total intensity in the sky at 1 degree. And in the first column, you see the real data at sub-degree scale. In this case, it's 12 arcminutes. So these are just the small scales. So we just remove from the total map the large scale. So these are just the small scales, the one that the neural network tried to reproduce. And this is the combined map. So small scales plus large scales. These again are real data. And on the right, you see the small scales generated by the neural network. You see that the network is able to understand the main feature, but remember that the goal is not to reproduce exactly the same pattern, but to reproduce something which has the same statistics, the same non-Gaussian statistics in the sky. So this is the pattern reproduced by the neural network, obtained by the neural network, and when we combine this pattern with the real scales, with the real large scales, you see that we get this map, which looks pretty similar and to the real one. If we try to analyze a bit more this data, we can do several stuff, and I'm still in the phase where I'm trying to validate these results that I get. But here you can see two examples. So this is the power spectrum of the patch that I showed you before. So the gray line here is the power spectrum of the patch just with the large angular scale. The blue line is the power spectrum of the real data at 12 arc minutes. And the orange line is the power spectrum of the combination of small scales coming from neural network and real large scales. And you see that the two power spectra match pretty well. Of course, we want, as I said, the goal here is to obtain something which is non-Gaussian. So we want to understand also the behavior of the higher order statistics. And here I show you the Minkowski function, which is a statistic that tells you different properties of the maps. And the goal here, again, we would like the real data to match well with what we obtain from the neural network. So these are the three Minkowski functional for real data, again in blue, just the small scales, and for the one obtained with the neural network. And you see that the neural network is really able to reproduce the statistics of real data. So this is in total intensity. Of course, all of this is to obtain actually observation, to obtain actually simulations in polarization. In polarization, the situation is a bit different because in total intensity, as I said, we have some regions of the sky where the sensitivity is good enough to allow us to go to small scales. In polarization, we don't have it. We don't have any region of the sky where we can trust our data at angular scale smaller than 1 degree. So we cannot do a train directly in polarization, but what we can do is making the assumption that the statistics of small scales foreground is the same in polarization and in total intensity. So we train the network by feeding it with large scales polarization map, this one that you see here, and we ask the network to produce small scales which have the same statistics as the temperature one. So this is the assumption that we do. And here you see the results. So this is the input and this is the output of the neural network. So you see that the neural network is able to put small scales on top of the large scales that we have. These are, of course, simulated small scales. We cannot say whether these are the correct pattern, but we hope that they have the correct statistic. And this is for the Stokes QNU maps. This is the polarized intensity, and this is the polarization angle. And you see that the pattern and the small scales that the network reproduce, at least if you look at them by eye, seem pretty realistic. And here I'm showing you another two kind of plots. So here is again the power spectrum of this map that we obtain, these maps that we obtain with the neural network in polarization for the E-modes and B-modes. And so the gray line here are the real data at 1 degree, and the color line are the neural network maps at 12 arc minutes. So we don't have data to compare, but we see that the function, the behavior of the power spectrum as a function of the multiple seems to be the one that we expect. So it follows somehow a power law. And here I'm just showing you the histogram of the Stokes QNU maps, just to show you that the small scales that we get. So this is the histogram just of the small scales, to see that we are really able to plug in small scales which are non-Gaussian. So I think it's over. These are my final remarks. I hope I convinced you that the detection of the signature of the inflation into the CMB polarized signal is one of the greatest goal that we have nowadays in observational cosmology, but also in fundamental physics. We have a huge experimental effort to try to achieve this detection in the coming decade. And experiments are not limited by sensitivity at the moment, but really by our knowledge of foregrounds. And one way to try to get realistic models of foreground on which to test our component separation algorithm and our pipeline for the CMB observation is to use neural networks.